In this video, we'll study the control of motors. Control of DC motors. So the starting current taken by a DC motor during the starting period of the motor, it is limited to a value by the resistance of the starter. So the starting current is equal to the normal rated current. So due to the starter, there is considerable loss of energy at the starting resistance. So if a single motor is started by a resistance starter, then the average value of the current during the starting period is limited to I, which is the normal full load current. So we have the supply voltage given by V equal to EB plus IRM plus IR, where EB is the back EMF developed in the motor, I is the current drawn by the motor from the supply, RM is the resistance of the motor, which is equal to RA plus RSC, that is armature resistance plus series field resistance. R is the resistance of the starter or starting resistance. So at any point of time, the supply voltage is given by this expression. So at the instant of switching on the supply, before the motor is started, the back EMF of the motor is 0 and it starts to build up from 0. So at the instant of switching on the supply, EB is 0 and a current of I amperes is drawn from the supply, and therefore the supply voltage V is given by the equation IR plus IRM, that is supply voltage is sum of the IR drop in motor armature and the voltage drop across the starting resistance. At any other time instant during the starting, the supply voltage V will be equal to the back EMF in the motor plus the drop in the motor plus the voltage drop in the starting resistance. And at the end of the accelerating period, the back EMF will be developed to the full instant and the supply voltage will be therefore V equal to EB plus IRM, since the starting resistance will be cut off to 0. So at the end of accelerating period, the value of R will be 0, that is the starting resistance will be 0, which is gradually cut off from the instant of switching on the supply. So we have V equal to EB plus IRM, where V is the fully developed value of back EMF. If T is the time in seconds for starting, and if we ignore the voltage drop due to the resistance of the motor armature, then we have the total energy supplied given by VIT watt seconds. So the figure shows voltage during the starting of the DC motor. So it is voltage of power plotted versus time. So we have the voltage across the starting resistance, which is high during the starting period, and we can see the back EMF is 0 and it is gradually increasing, and we have the full back EMF value, which is at the end of the starting period, that is at the end of accelerating period, and this is the full supply voltage. And we have the voltage drop in the motor armature, which is the constant throughout the starting period. So as seen in the figure, we can notice that the back EMF at the starting period is 0 and voltage across the starter resistance is high. And back EMF is gradually developed and we get the full back EMF at the end of the starting period, whereas the voltage across the starting resistance is 0. So in this figure, we can see the starting of the DC motor by using the resistor in the armature circuit. So we have the term EB, which is the back EMF, and VR, it is the voltage drop across the starting resistance at any instant. So we have EB, it is the back EMF, and VR is the voltage drop across the starting resistance. So as seen in the figure, we can deduce that the energy wasted in the starting resistance R is the area in the diagram, the upper part. So we have it as half VIT watt second. So the efficiency of the starting is 50%. Next topic is series parallel starting. So in the traction work, usually 2 or more motors will be employed which are similar in characteristic. So considerable energy saving can be achieved by using series parallel starting. The figure shows the series parallel starting for the 2 motors. So the 2 series motors used, they will be connected in series with the starting resistance. So gradually this starting resistance will be cut off in steps and the back EMF will be developed from 0 to half the supply voltage minus the IR drop. Since the series motors are connected in series connection, the voltage drop across the 2 motors will be V by 2. Therefore, the back EMF is equal to V by 2 minus IR. So once the starting resistance is cut off completely, the motor are in full series position and it gives a running speed. And we have the second connection of motors in parallel position where the starting resistance is reinserted to the circuit. So this starting resistance will be again cut off in steps and the back EMF of each motor will develop from the value V by 2 minus IR to the normal value. So back EMF will be fully developed to V minus IR. So once the starting resistance is cut off completely, the motors will be in full parallel position and it gives another running speed. So this speed is greater than the speed when the motors are in full series position. As shown in the figure, let the current during the starting interval be limited to the normal rated current I per motor. So the starting current is limited to the normal rated current, which is I per motor. So as seen in the figure, during the series period, a current of I amperes is drawn from the supply, whereas during the parallel period, current of 2I amperes is drawn from the supply. Figure shows the voltage build-up in series parallel starting. At the instant of starting, OA equal to OB, which is equal to IR drop in each motor, since there is no back EMF developed at that instant, and OK equal to supply voltage V. The back EMF of the two motors, it jointly develops, and at the point E, the back EMF of the two motors plus IR drops is equals to voltage V. At any point on the line EC, at any instant, gives the sum of back EMF of the two motors and the IR drops. OE denotes the time taken for the series period, and at instant E, the motors are switched to parallel and the starting resistance is reinserted. At the instant E, that is at the end of series period, each motor has developed a back EMF which is equal to V by 2 minus IR. The back EMF of each motor, it is represented in the figure by the ordinate EL, which is equal to ED minus LD, that is equal to V by 2 minus IR. The back EMF of the motor combination now develops along the line LG, and at the point H, when the motors are in full parallel position, we have HF equal to supply voltage V, HG is equal to the normal back EMF of each motor, and GF equal to IR drop in each motor. Figure shows the current during the series and parallel starting periods. So we have current plotted with respect to time. So during the series period OE, the current is I, while during the parallel period EH, the current is 2I. The time during which the motors remain in series position is Ts, and the time for which the motors remain in parallel position is Tp. So this can be determined from the previous figure, where the triangle OLE and OGH are similar. So we have therefore OE by OH is equal to LE by GH, that is TS by T is equal to LE by GH, which is equal to DE minus DL by DFH minus FG. So we have Ts by T equal to V by 2 minus IR by V minus IR. So we have Ts equal to half into V minus 2 IR by V minus IR into T. So we have Ts plus Tp equal to T as shown in the figure. Therefore, Tp is equal to T minus Ts, that is T minus half into V minus 2 IR by V minus IR into T. Therefore, Tp is equal to 1 minus half into V minus 2 IR by V minus IR into T. To calculate the efficiency of the series parallel starting method, we neglect the IR drop in the armature circuit and back EMF is developed practically equal to the voltage impressed across the motor. This modifies the figure of voltage buildup in series parallel starting to the figure as shown. So this figure can be used to find the efficiency of the series parallel starting. As shown in the figure, D is the midpoint of CE and the back EMF of the motor, it develops along the line DF in the parallel combination. We have Kc equal to Cf, that is the time duration for series combination is equal to time duration for the parallel combination, that is Ts equal to Tp. Let us consider Ts equal to Tp equal to T and the average starting current for the two motors is I amps, that is it is I per motor. From the figure we have Ts equal to OE and Tp equal to EH. So the energy lost in the starting resistance it is given by I into half V into T plus 2I into half V by 2 into T, that is half VIT plus half VIT, which is equal to VIT, and the total energy supplied is equal to VIT for the series combination plus V into 2IT for the parallel combination, that is equal to 3 VIT. Therefore, the efficiency of series parallel starting is equal to energy supplied minus energy lost by the total energy supplied, that is equal to 2 by 3 or it is 66.67%. So the efficiency is increased by about 17%. So the series parallel method, it results in a savings of about 15 to 20% in the energy. If there are more number of motors, the efficiency is increasing. So if there are 4 motors, then the efficiency is around 73%. Next topic is series parallel control. So the series parallel control can be carried out by two methods. One is shunt transition and another is bridge transition. So the figure shows the various stages in the shunt transition method of series parallel control. So this is the shunt transition method of series parallel control. So the two motors are connected in series and a starting resistance is inserted. So in steps 1 to 4, this starting resistance is cut off gradually while the motors are accelerated. So as the starting resistance gradually cut off, it is brought to zero position, that is at step 4, where the motors will be now in full series position. During the transition of the motors from series to parallel, the starting resistance will be reinserted in the motor circuit. That is shown in the step 5. So the two full series position motors have the starting resistance reinserted, and then the one of the motor is shorted, that is bypassed, that is shown in 6th step, and this motor will be disconnected from the main circuit, which is shown in step 7, and in step 6 the motor is connected in parallel with the first motor, giving the first parallel position of the motors, and the resistance will be gradually cut off in steps and the motors will be then in full parallel position. This method is known as shunt transition method. So from steps 1 to 4, we have the series position of motors where the two motors are connected in series and the starting resistance is gradually cut off to 0. And then from series to parallel transition of the motors, the starting resistance is reinserted to the circuit, that is shown in step 5. And then in step 6, one of the motor is shorted and it is disconnected from the supply in steps 6 and 7. In step 8, the motor terminal which was disconnected from the supply is connected to the other motor terminal, making the two motors in parallel connection, that is in step 8. So it gives us the first parallel position of motors, and later on the resistance will be gradually cut out in steps and the motors will be in full parallel position. This method is known as the shunt transition method. Next method of series parallel control is bridge transition. So in this method, the motors and the starting rheostats, they are connected in the form of Wheatstone bridge as shown in the figure. The first figure is the series position. So at starting, the motors are in series with the link P in position AA dash, and the motors will be in full series when the link P is in position BB dash. So In the first starting position, the motors are in series and the rheostats, they are completely in the circuit as indicated by the rheostat arm P at A' position. A and A' they are moved in the direction of the arrowhead, and in the position B B', the motors will be in full series position. Next figure is for the transition step. So in this transition step, the rheostats, they are reinserted by connecting it to positive and negative of the supply as shown in the figure B. And the next figure is for the first parallel position. So in the first parallel position, the link P is removed and the motors are connected in parallel with the starting resistance included in the circuit. Later, the starting resistance will be gradually cut off and the motors will be in full parallel position. The advantage of this bridge transition method over the shunt transition method is that the normal accelerating torque from both the motors is available throughout the starting period compared to shunt transition method where there is high fluctuation in the torque, and hence the acceleration is smoother in bridge transition method, whereas in shunt transition method there will be jerks caused. Next topic is drum controllers. For the series parallel control methods, that is shunt transition and bridge transition, series parallel drum type controllers are used. So these controllers along with transition has the following arrangements. They are starting, reversing and braking of the motors. So these series parallel drum type controllers along with transition of motors from series to parallel position, it will be also having the arrangements for starting the motors, for reversing the motors and braking of the motors. Let us see the problems related to series parallel starting. First problem, a motor coach bogie having two series motors is accelerated uniformly to a speed of 48 km per hour in 30 seconds with the help of a series parallel controller. If the average tractive effort per motor is 13,350 newtons, calculate the approximate loss of energy in the starting rheostats. So we have Vm equal to 48 km per hour and the time duration is 30 seconds, that is T1, and tractive effort per motor Ft is 13,350 Newton. So Ft, the tractive effort for the two motors is 2 into 13,350, that is 26,700 Newton. So the useful energy for acceleration is equal to half FTVM by 3600 into T1 by 3600 in kilowatt hour. So we get the useful energy equal to half into 26,700 into 48 divided by 3,600 into 30 by 3,600. which is around 1.483 kilowatt hour. The loss of energy in the starting rheostats, or the energy lost in the starting rheostats, is equal to half of the useful energy. That is equal to 1.483 divided by 2, that is 0.741 kilowatt hour. Next problem. A multiple unit train weighing 175 tons is equipped with 6 motors giving a total tractive effort of 69,000 newtons. The motors, they operate at a line voltage of 600 volts, and each motor takes an average current of 200 amps during starting. Series parallel control method is used for starting. The full line voltage is applied to each motor when the speed reaches 38.6 km per hour. Determine the energy supplied during the starting period, energy lost in the starting resistance, and the useful energy supplied to the train. Each motor has a resistance of 0.15 ohms. So we have W equal to 175 tons, and we have 6 motors. The total tractive effort Ft is 69,000 newtons, and the voltage is 600 volts. The current drawn per motor is 200 amperes, and the maximum speed Vm is 38.6 km per hour, and the motor resistance is 0.15 ohms. We have Ft equal to 277.8 We alpha, because during the starting period the tractive effort is required. So the starting period is nothing but the accelerating period. So the tractive effort required for the accelerating period is 277.8 We alpha. Hence the tractive effort for the starting period Ft is equal to 277.8 We alpha. Since the rotational inertia effect is not given, consider We equal to W. Therefore, we have 69,000 equal to 277.8 into 175 alpha. Therefore, the acceleration alpha is given by 69,000 by 277.8 into 175. We get the value around 1.42 km per hour per second. Next, we have the time for acceleration, that is T1 equal to Vm by alpha, that is 38.6 by 1.42. It comes around 27.2 seconds. We have Ts equal to half T into V minus 2IR by V minus IR. So we have Ts equal to half into 27.2 into 600 minus 2 into 200 into 0.15 divided by 600 minus 200 into 0.15, where T is the time for acceleration. So we have Ts equal to 12.9 seconds. We have Tp equal to T minus Ts. that is 27.2 minus 12.9, that is around 14.3 second. Next we have the total energy supplied to be found for both series position and parallel position. So first we have series position where two motors are in series and there are such three circuits in parallel. We have the energy supplied in series position given by 3 VITs, that is 3 into 600 into 200 into 12.9, which comes around 4.64 into 10 to power 6 watt second. Next is for parallel position, that is when all the motors are in parallel as 6 different circuits. So we have energy supplied given by 6 VITP, that is 6 into 600 into 200 into 14.3, which comes around 10.3 into 10 to power 6 watt second. Therefore, the total energy supplied is equal to 14.94 into 10 to power 6 watt second. The total energy supplied in kilowatt hour is 4.15 kilowatt hour. Next is energy wasted in the starting resistance. So for series position, we have the energy wasted in the starting resistance as 3 into V minus 2IR by 2 into I into Ts, that is 3 into 600 minus 2 into 200 into 0.15 divided by 2 into 200 into 12.9, that is around 2.09 into 10 to the power 6 watt second. Next is for parallel position. We have the energy wasted in starting resistance equal to 6 into V by 2 by 2 into I into Tp in watt second, that is equal to 6 into 300 by 2 into 200 into 14.3, that is equal to 2.57 into 10 to power 6 watt second. Therefore, the total energy wasted in the starting resistance is the energy wasted in series position plus the energy wasted in parallel position, that is equal to 4.66 into 10 to the power 6 watt second. This is equal to 1.29 kilowatt hour. The energy lost in the motor resistance is given by 6 I square R T, that is 6 into 200 square into 0.15 into 27.2, which comes around 0.98 into 10 to the power 6 watt second, which is equal to 0.272 kilowatt hour. Next is useful energy supplied to the train. It is given by the equation half Ft Vm by 3600 into T1 by 3600, that is half into 69,000 into 38.6 divided by 3600 into 27.2 by 3600, which comes around 2.79 kilowatt hours. Next problem. An electric train weighing 132 tons is equipped with four 600-volt motors arranged in two pairs for the series parallel control. If during series parallel starting, the current per motor is maintained at 400 amperes, estimate the duration of the starting period, speed of the train at transition, and the rheostatic loss during series and parallel steps of starting. At 400 amperes and 600 volts, the tractive effort per motor is 19,270 Newton and the train speed is 39 km per hour. Assume that the train is started upper gradient of 1 in 100 and the resistance to traction is 44.5 Newton per ton. Allow 10% for the effect of rotational inertia. Each motor has a resistance of 0.1 ohm. So we have W equal to 132 tons and we have 4 motors. The supply voltage is 600 volt and the current is 400 amperes per motor. The tractive effort per motor is 19,270. The train speed Vm is 39 km per hour. The gradient is 1 in 100, so it is percentage gradient is 1. The train resistance R is 44.5 Newton per ton. 10% is allowed for rotational inertia, so WE is equal to 1.1 times W and motor has a resistance of 0.1 ohm, so R equal to 0.1 ohms. So we have tractive effort Ft equal to 277.8 WE alpha plus 98.1 WG plus WR. So the value of tractive effort FT is equal to 19,270, which is tractive effort per motor, into the number of motors 4, which is equal to 77,080 newtons. So substituting the values in the equation of FT to find the value of alpha, we have 77,080 equal to 277.8 into 1.1 into 132 alpha plus 98.1 into 132 into 1 plus 132 into 44.5. Solving, we get the value of acceleration alpha as 1.44 kilometer per hour per second. So the time duration for acceleration period, the time duration for acceleration period is given by T1 equal to Vm by alpha. So we have the value of Vm equal to 39 km per hour by alpha 1.44 km per hour per second. So we get the value of T1 as 27.08 seconds. We have Ts equal to 1 by 2 T into V minus 2 IR by V minus IR. So here T is the time for starting period, which is T1. So we have Ts equal to half into 27.08 into 600 minus 2 into 400 into 0.1 divided by 600 minus 400 into 0.1. So we get the value of Ts as 12.57 second. So the speed at transition, it is given by alpha t, that is alpha t, which is alpha ts. So we have alpha value 1.44 and ts is 12.57. So we get the speed at transition as 18.1 kilometer per hour per second. We have Tp equal to T minus Ts, that is equal to 27.08 minus 12.57, that is Tp value gives us as 14.51 second. Energy lost during the series period. So we have the two motors in series and such two circuits are in parallel. So assuming two motors in series and there are such two circuits in parallel. So we have energy loss during series period equal to 2 into V minus 2 IR by 2 into I into time duration Ts. This is in watt second. So substituting, we have 2 into 600 minus 2 into 400 into 0.1 divided by 2 into 400 into 12.57, that is equal to 2 into 600 minus 80 by 2 into 400 into 12.57 divided by 3600 into 1000 in kilowatt hour. So we get the answer as 0.726 kilowatt hour. Next is energy lost during the parallel period when all the motors are in parallel as 4 circuits. So we have energy loss during the parallel period given by 4 into V by 2 by 2 into I into Tp in watt second. So we have 4 into 300 by 2 into 400 into 14.51, that is we have 2 into 300 into 400 into 14.51 divided by 3600 into 1000 in kilowatt hour. We get the answer as 0.967 kilowatt hour.